Welcome to the lecture on classical planning, which is a topic in learning from examples in machine learning subject. So we shall see the PDDL for any kind of plan. Let's start with our lecture. What is planning? When I'm saying planning is nothing but you're trying to just put a sequence of actions or plan of action to achieve one's goal. If you are planning to go to a picnic, then you'll decide the spot where you're going to visit. Then you'll try to find out the mode of transport. So the day will come when you should start a picnic. In the morning, you'll wake up, um, get ready to go to that picnic, get onto the transport, and then pack some things. You'll pack some things at home, and then get on to the transport, and then you'll reach the picnic spot. So these are the action sequence which you are performing for going to a picnic spot. In the same way, in this machine learning or using these things, using these techniques, you'll try to write some action, and you'll go in that sequence so that you'll reach your goal. What is classical planning? When you're coming to the concept of classical planning, it is nothing but sequence of actions to achieve a goal. And here you are having different types of environments, fully observable environment, where each and every fact, you know each and every fact about the problem or about the environment. So that when you are trying to find a solution, it will be very useful for you in which direction should you go. Deterministic. You are quite confident about the result that if I do this action, then this result will occur. Such kinds you are calling it as deterministic. And the other one is static, where the things does not change. And discrete means unique things will be present. Unique things will be present in the environment. And the next slide, you are seeing the challenges in planning with standard search method. What are the challenges? Sometimes, if you are taking anything, you can see that there are many irrelevant actions. There are many irrelevant actions, and which will try to deviate you from reaching your goal. So, if you are goal oriented, then you can reach your goal. And it is also very difficult to find a good heuristic function. Here, when I'm saying the word heuristic or when I'm using this word heuristic, the intent behind this heuristic is the measure of appropriateness, whether it will take you to the goal node or not. And the other one is the language for, there is a language is also there for planning. And this language will make it easy for algorithms to exploit the logical structure of the problem. Whatever may be the structure, that structure of the problem is found out easily, or you're trying to find out the solution in a easy manner by using PDDL. And what are the challenges? You can just see in the form of a figure. Here we have started. And after starting, you may want to go to pet store, you may want to go to school, you may want to go to supermarket, and you may want to sleep, or you'll just read a book, or you may sit in a chair, or you can watch a movie, or you can do some homework. So in this way, you have many tasks, and each task is having again some subset of tasks. Like if you go to a pet store, you'll talk to a parrot, and then you'll buy a dog. If you go to school, you'll go to the class, and if you go to supermarket, there you'll buy different food items or any stationery items or whichever objects are related to the home. And when you're going to bed, you just sleep. You don't do anything. And if you're reading a book, you'll open the book and read. And you'll when you're sitting in a chair, you'll just sit. So these are different things. And from it, how many, there are too many choices, as you can see in this figure. And how do you select the thing? You select the thing based on its appropriateness. Now, we shall see a language which is helping us a lot. That is, which action should be, it helps us to choose the action. Which action should be chosen in which state so that you can reach your goal state. So here in the planning domain definition language, PDDL, the full form is planning domain definition language. And in this domain definition language, you have two important things. One is state, the other one is action. Coming to the first thing, state is represented by a conjunction of ground atoms without function symbols. Here, ground atoms means at of truck 1, comma LSU, and at of truck 2, comma downtown. Both of these are ground atoms. And no symbols are taken here. And inverted V is nothing but a conjunction. It's a kind of proposition which is true when both at of truck 1 is at LSU and truck 2 is at downtown. Then only it is true. Otherwise, it is false. That is conjunction. So in this way, you are trying to write your state and action. Action fly. Fly is an example or instance for an action. When you are flying on a plane, there should be a plane P and there should be some destination, sorry, starting point where we are going to start our journey. If I'm going to start from Vijayawada, I will start from Vijayawada and reach Dubai. To Dubai. Plane will be traveling from Vijayawada to Dubai or Vijayawada to Hyderabad. So from is the source or the starting point and to is the destination. For it, first of all, I should have a plane in the starting point. Airport should be there, plane should be there, and an airport should also be present at the destination point. Then only the plane will fly from starting point to the destination point. And effect is the plane will reach from Vijayawada, the plane will reach the destination. It may be either Dubai or Hyderabad or so. So a specific planning problem. You see that it is having an initial state and it is having a goal state. Goal state can be given with the positive as well as negative things. That means it is a conjunction of literals. That is at and you have seen it the previous slide, and you'll try to write it in that way. And you'll also have a set of action schemas. And clearly, a planning problem can be seen as a such problem. Let me give some explanation regarding precondition and effect of an action. This precondition and effect, both of them are conjunction of literals. Either they may be positive or negative atomic sentences. Atomic sentence means a single sentence which is trying to tell us a single fact. There are no combinations in it. Only one single sentence will be there. And precondition defines the states in which the action can be executed, and the effect defines the result of executing the action. Precondition means it should be the state where the action can take place. So here, if the plane is at the starting point, then only you can fly the plane from the starting point. If the plane is not there, if airport is not there, then fly action cannot take place. And after the action had been executed, it will reach some destination. And an action A can be executed in status if S entails to the precondition of A. Precondition of A is satisfied, then action A will be done or executed, and S dash or child state will be generated. That is another kind of state. And entailment can be represented like this: S to Q. So if and only if positive literal in Q, conclusion is Q. S is precondition. So if this thing is done, then it will result in either it may result in Q or it may not result. Excuse me. Notation: A belongs to action of S. That means A is an action in state which can be applied upon state S. And S is state which will be satisfying the precondition for A. If that precondition is satisfied, then action A will be applied on state S and the action will be completed. And where any variables in A are universal, here you can see that all the variables are universally quantified. And for example, for all P, that is universal quantification means that should be true for all the values, or that will be hold true for all the values. For all P from comma to, fly of P comma from comma to belongs to action. Plane should be at from, and P should be a plane, and from should be an airport, and to will also be an airport. Next is an action is applicable in status if preconditions are satisfied by S. So an action is applicable if the preconditions are satisfied by S. And when an action schema A contains variables, it may have multiple applicable instantiations. For example, with the initial state defined in the fly action, you have either it may fly from Hyderabad to Vijayawada or Vijayawada to Hyderabad. Or here you can see that it is San Francisco to JFK or JFK to San Francisco, both of which are applicable in the initial state. And if an action A has V variables, then in the domain with K unique names of objects, how much time will it take? It is going to take big O of Vk time. How much time will it take? Big O of Vk. K means the unique names in the objects, V means variables. And worst, this is the worst case, which we are using to find the applicable ground actions. So to propositionalize, that is, we are going to use propositions like at, fly, so on. These are the propositions. You're replacing each action schema with a set of ground actions, and a SAT plan will be prepared. And here, if V and K are large, it is very impractical for classical planning. And result of executing action A in state S. When I am executing an action in a status, it is defined as a status which is represented by set of fluents. The fluents are used formed by starting with S and removing the fluents that appear as negative. If at all any action appears to, if any fluent appears to be negative, then you're going to delete it. Otherwise, if it is done, then you're going to add it. If it is done, you'll add it. If it is completed, it will try to delete it. Uh, the child state will be added and the parent will be deleted, or it may be negated. So these are the two things done here. And you're adding the fluents that are positive literals in the action effects. And result of S comma A equal to S minus. That means you have applied the action on status. So action A will be deleted and the other action will be, whatever you have done will be added. So here, if I'm doing this action fly, P1, comma San Francisco to JFK, we would remove at top because we have flown from SFO to JFK. At plane P1 is at SFO will be removed because plane is not in SFO, but plane is added at JFK. And here we need subscripts for time and successor state actions on the form FT plus 1. Action causes FT or FT, and not action causes not FT. T plus 1 is the next state, T is the current state. In PDDL, the times and states are implicit. Here we need not say. If it is written in the other one, then it is antecedent, it's next thing, and the other one is previous thing. And precondition always refers to time T and effect to time T plus 1. Precondition will refer to time t and it will affect to time t plus 1. And a set of action schema serves as definition. If you are taking a action schema, it will have a planning domain and specific problem within this domain is defined with the addition of initial state and goal state. Though, so you have seen initial state is also conjunction like at of p comma SFO and plane B, and variables are treated as existentially quantified. So this goal is to have any plane at SFO, and problem is solved when we can find a sequence of actions which will take us from SFO to JFK. And we also gave an example here: state rich and famous and miserable entails goal rich and famous. If they are rich and famous, both this is a goal. And if plane is at P1 is plane and it is at SFO, then you say that goal is plane at of P comma SFO and P is a plane. Let me explain a small example using this PDDL, planning domain definition language. You can see the initial state, the goal and action. The initial state is uh, the CF cargo. Cargo. You're trying to transport a cargo from one airport to another airport using the planes. So here, if you see, C1 is at SFO, cargo C1 is at SFO, and cargo C2 is at JFK, and P1 plane is at SFO, and P2 plane is at JFK, and JFK and SFO are airports. Goal is the cargo will be C1 will be which is at JFK, and that means C1 should travel from the other one to JFK, and this cargo will be the cargo which is at SFO will be transported to some other place. So here action. In order to transport the cargo, I need to perform three actions. One is loading, the other one is unloading, and the other one is flying. So you need to load the plane with the cargo, and then after reaching destination, you'll unload the plane. The first thing is you need to travel or fly from starting point to the destination. So precondition for loading is cargo should be at A. If I have to load the cargo into a plane at airport A, then cargo should be there at airport A. And plane should also be there at airport A. Then only I can load the cargo into the plane. Otherwise, I cannot load precondition. If I have loaded, then the cargo will not be in the airport, but it will be in the plane because it had been taken from the airport and it had been loaded into the plane. So negated. Act of C comma is negated. Initially it was true, and now after the action had been performed, it is negated, and in will be added. It has been deleted and in is added. In means that is your cargo is in plane P. Unloading. When you're unloading, the cargo will should already present in the plane. Then you can unload it to the airport. So the cargo is present in the plane and you are trying to unload it into the airport. Precondition is in of C comma P. Cargo is in the plane. And what are you trying to do? Your plane is at airport, and then you can perform the action unload. After you have performed the action unload, what is happening? The cargo will be unloaded from plane to the airport A. So at of C comma is true and in of C comma P is false. So it is negated. Another action, if you see, fly of P comma from comma to. Plane P will fly from the airport from to the airport to. For it, the plane should be at airport from, and then it will reach to the airport to. Effect of this action is the plane will reach airport too. So this is PDDL description of an air cargo transportation planning problem. With this, I end my lecture. Thank you.